sort of more abstract science. Let me reverse engineer from there and say that, where we're going is technology, usable technology. And I would say that there's already been a quantum technological revolution. If you think that quantum technology is just entering your life now, that would not be correct, in my opinion. You've been enjoying, many decades of quantum technologies that are intimately present in your life, from the humble transistor to the laser, to life-saving innovations like MRI machines, to the computers and phones that are present, all around you, even in your pocket at any given moment. Okay, so all of these technologies depend in some way, subtle or in intricate ways, on quantum mechanics and quantum theory, and these would be impossible without them. So please don't think that quantum is something on the horizon. Quantum is very much already here in terms of something that is in your life. Okay? It's not just a theory, and it's not just something that's a source of emerging technologies. It's very much omnipresent already. Okay? And of course, here's the humble computer, and the computer is a place where I want to maybe take a leap into the quantum technologies that are coming, which you could sort of refer to as quantum 2.0. So I think if there's a poster child for quantum 2.0, it is the quantum computer. And that's an interesting thing to say, given that I just said that ordinary computers are very much quantum technology. So there must be something more quantum happening in quantum computers. So I just wanted to disambiguate that. But here's a popular sort of illustration of a quantum computer that's been going around. You see this image in many different talks and presentations. And I think it captures the look and feel of current quantum computers, especially superconducting ones. This kind of looks like a chandelier. In fact, it's becoming more and more referred to as that. Most of what you see here is wiring and refrigeration. The actual quantum bits or qubits are in the can at the bottom of this device. And as I said, I want to hammer home the point about refrigeration. Being able to manufacture quantum bits is a kind of revolution in and of itself in terms of electrical engineering and what we call device physics. But the unsung hero of this picture, of this whole story, is refrigeration. These, again, in the superconducting approach to quantum computing, these qubits are super cooled, usually to as low as 8 or 9 millikelvin. So that's colder than the vacuum of space, and it would not be wrong to say that when you are close to, say, an active quantum computing hardware stack, you are next to the coldest point in the universe. So just keep that in mind. In any case, this device has this type of device has captured a lot of attention, both within science and outside of it in the last sort of 5 years, I would say, especially. There was probably a moment in 2019 when Google had made an announcement about their superconducting machine named Sycamore, which at the time had 53 qubits at its disposal, where they had pushed through a certain kind of calculation that classically, was at least thought at first to take even thousands of years on an quote unquote ordinary supercomputer, where they were able to do this instead on their Sycamore machine within less than 3 minutes. I mean, there was a lot of debate about that result when it came out, and then there were counter claims that you could do those calculations classically in maybe as little as 25 hours if you done them in a more clever way, at least on the classical side. Although standing back from it, there's still a big difference between 25 hours and something like 2.5 minutes. But however you feel about that, it generated a lot of interest in quantum computing at a particular moment. And there's really been a massive, I think, upward tick in capabilities of this kind of hardware, again, even in just the past few years. So just as another image, and maybe with a more sense of human scale here. Okay, so here's a quantum engineer. She's working on a very similar setup. This is another superconducting device. I keep saying superconducting because there are different modalities of quantum computing. You have, in addition to these superconducting transmon chips that are maybe best represented by companies like IBM, Google, Rigetti Computing. If any of you have heard of Rigetti Computing, by the way, the founder of that, Chad Rigetti, even though it's an American company, is actually from Saskatchewan, from nearby Moose Jaw. But those are emblematic of the superconducting quantum computing world. There's also trapped ion quantum computing, neutral atom quantum computing, photonic quantum computing. So there's different modalities, and they have different strengths and different weaknesses as well at the same time. We have not converged on any single architecture here. The future may be some combination of these. None of these have achieved scalable or fault-tolerant quantum computing. For those of you who are a little bit, maybe in the know about such things. But I would argue that we have devices currently that can compute in a quantum-driven way, that utilize quantum information processing, even if they're not scalable to any, say, size or dimensionality of problem, and even if they're quite noisy at this time. And I think that just to dispel some of the mystery around qubits or quantum bits. If you think about the bits that are in your, in your phone or your ordinary computer, they are essentially on-off switches: 0, 1, on-off, true, false. And it's amazing what we can do with that. If you have a few billion of those bits at your disposal, there's a lot of processing that you can do. However, a quantum bit, to be absolutely reductionist about it, is like a dimmer switch. It's on, off, 0, 1, or anything in between. In fact, that anything is not even just one dimensional of anything, but it's for those of you who heard of the Bloch sphere, it's more like a sphere where you have on and off as two different points. Depending on your model, it might be diametrically opposite, two different points on the sphere, but you can have any other state as well is perfectly admissible, at least while a quantum program is running. At the end, there's a collapse to 0 or 1, the classical states. But in between, you have access to all of these superposition states. So even with a single qubit, you have access to an infinitude of superposition states, which are combinations, if you like, normalized combinations, normalized linear combinations of 0 and 1. And this brings with it the ability to enact logic gates. So, in ordinary computing, you have logic gates that manipulate bits, whether it's a single bit or a register of many bits. Flipping them from individual bits from 0 to 1, sometimes in a controlled way. Sometimes you might have a controlled NOT gate where I'll only flip a bit if another bit is on, for instance. And so, but these are the basic logic gates, and you have all of those at your disposal in quantum computing. But you also have gates that were not possible before. The Hadamard gate is probably the bread and butter example. It's a gate that will put a qubit in a superposition. An equal superposition of 0 and 1. It has to be normalized, if you think about it in terms of as a vector, in terms of linear algebra, but nonetheless, it can create an even superposition that's basically the sum of 0 and 1. You can also, and you could consider that constructive interference if you want to think about this in terms of wave theory. But you can also have destructive interference. You can have 0 minus 1, which is another Hadamard state. And this combination of constructive and destructive interference of these basic computing states allows you to accomplish information processing that is simply unavailable to you in classical computation, or computation based on classical physical rules. And that's even just with a single qubit. The moment I introduce two qubits, now I can talk about entangling them. And then there's a whole other dimension of computing possibilities right there. I don't want to go too much into quantum entanglement, but the point is that even a single qubit is massively powerful in some sense compared to collection of however many ordinary bits. And then when I bring a second qubit into the mix, now all of a sudden I can try to access further quantum mechanical properties to enhance my information processing. And by the way, the ability to generate quantum entanglement on the fly, which is this machine that you see on screen, in a sense, can do that as an entanglement generator. That is maybe part of the distinction between quantum 2.0 and quantum 1.0. At quantum 1.0, we were able to take advantage of certain very simple quantum mechanical properties. At this stage, we are trying to access deeper quantum mechanical properties, and being able to generate entanglement even in the laboratory was not something that was necessarily possible before, say, the 1980s. Again, for those of you who follow Nobel Prizes in physics in 2022, you could say that Nobel Prize was for the controlled generation of entanglement, at least in a laboratory setting. And in some sense, we've gotten very, very good at that with these superconducting devices. Okay. Well, that's in some sense, that's quantum computing in a nutshell. And again, what you just saw is very different from this. I'm not going to try and predict what a quantum computer might look like physically in 10, 20, 30 years. As we know, computers massively shrunk from, over the period of many decades, from room-sized devices into, what you see here on screen now and your phone, even your watch. Think about that, if you have an Apple Watch or some other similar device, a lot of computing power packed into a very small space, a very small volume. So it's anyone's guess, right now you could say quantum computing is in its room-sized phase, and we'll see what happens in the future. I'm not so, again, I don't want to sort of wax lyrical about that or make predictions as much as put this up for posterity now, and we'll see in 30 years what's true or what's not. I'm just more interested in the basic functionality of a quantum computer and how we can improve that. Before we talk about that, I just want to tell you that quantum computers, even though they've captured a lot of the imagination, are not the only new technologies that are emerging. Quantum sensors are another very intriguing and potentially powerful platform, as well as quantum communications in general. That has an overlap with quantum computers, but if any of you have heard of like quantum key distribution and various experiments involving satellites, like there's the KeySat mission in Canada. It's a very, very interesting time, I think, for all of these technologies. Anyway, I just wanted to flag some of these for your further attention. Well, all of this is leading to a lot of this, okay, a lot of quantum mania. I think we're living in a really interesting time, which mirrors a lot of the general excitement of 100 years ago when the first attempts at quantum were the quantum 1.0. Let me put it like that was emerging. But what I firmly believe is that pushing all of these technologies forward, I'm going to focus on quantum computers, but pushing all of these technologies forward requires materials with new behaviors, new functionalities, or maybe I should say subtle behaviors. When I showed you that first illustration of a quantum computer, one of the first things I told you was that that these components of it are operating at temperatures below, well below 1 Kelvin. So you can think about a quantum computer actually as an extreme environment that's being created. Forget about it as a computer. Think about it as an extreme environment that is being created in the laboratory, and that pushes materials to an extreme as a result. At the same time, things like goals like mitigating quantum noise in such a machine. And achieving a kind of fault tolerance, again, requires materials that might have subtle or maybe even many different kinds of behaviors that can be activated depending on the current state of the machine or the current state of a computation that you're running. So what we really need are very adaptable materials that can exhibit in a very controlled way, in a very sustained way, designer behaviors and perhaps many different designer behaviors depending on what is occurring within the device. Okay. So that's what really drives us or takes us forward into the material science. And so, here's an article. It's funny to think that 2019 feels like yesterday, but also it's 7 years ago. So time is clicking on by. 2019 is the same year I invoked when I mentioned about Google's Sycamore machine. But anyway, here's just an article talking about some research that was published in Nature Physics, where at least one of the authors was coming out of Harvard. So this was Harvard's press release. And if you look at the bottom, this is about materials for quantum computing, and the type of material that they're focused on here is what's called the topological material. And at the bottom it says topological insulators are materials that can conduct electricity on their surface or edge, but not in the middle. So already that's a material that's exhibiting two kinds of behaviors at once. Parts of it are conducting, whereas parts of it are insulating, and that's happening all at the same time. And it says the strange thing about these materials is no matter how you cut them, and this is, okay, speaking of cut, the little, the line at the bottom is cut off a bit. It says no matter how you cut them, the surface will always be conducting and the middle will always be insulating. Okay. So this property of conducting in a certain zone and insulating another zone is completely invariant, if you like, with regards to the shape of the material or how it's been cut or sliced or prepared. So already there's some unusual physics happening in such a material, and the point of this article was that there was some desire to use these materials in a quantum information processing context where the functionality of the device might benefit from these two behaviors at once and the stability of those behaviors. Okay. So what's interesting about this is that topology, or topological, the adjective, but topology is a mathematical concept. Of course, there's a massive overlap between physics and mathematics. They're inseparable from one another. Certainly physics physics is written in the language of math. I think we can all agree upon that. Maybe what's less understood is that a lot of mathematics, even quote unquote pure mathematics, is influenced by concerns in physics. Maybe it gets abstracted and worked on in a solely or exclusively mathematical way, but nonetheless the inspiration came from questions or work being done in physics. So it's a two-way street. But it catches my eye as a mathematician by training to see topology in the title of something emerging from the condensed matter or solid state physics world. And topology, by the way, is the study of shape, which is a little bit different than geometry, by the way. In geometry, geometry is shapes where distance, angle, how you orient yourself, all of this really matters. Whereas in topology, you only care about the features that survive after stretching and squeezing. Like, I don't care about how far 2 points away are away from one another on a surface. All I care about is that maybe they can be connected by a path. Maybe that's all I care about. I don't care about the length of the path. So topology is a little bit weaker than geometry. And here's just another article, believe it or not, also from 2019. So that's clearly my favorite year for some reason. But in any case, just strange topological materials popping up everywhere physicists look. And here you see, if you stare at this, depending on the resolution of your monitor, you might see a honeycomb pattern here or not, sort of typical, telltale sign of something like graphene. But in any case, there's a lot of independent interest in topological materials. But I think that their main application could be likely be to quantum computing and the design of superconducting quantum chips and other related components. There was in fact even if you go, I mentioned the 2022 Nobel Prize in Physics a little bit earlier, but the 2016 Nobel Prize in Physics was actually for the theoretical prediction of of these topological materials, including topological insulators. So these were the three individuals who won the Nobel Prize that year. Thuless, unfortunately, had passed away just a few years ago. But each of these individuals had a hand in theoretically predicting that such materials should exist. And in fact, in the 2000s, about 8-9 years before this Nobel Prize, some of the first good examples were synthesized in laboratory settings, 2D and 3D topological insulating states. And here you see the Nobel Prize committee trying to explain topology to that year, to the to the world, if you like. So here they've taken to ripping, to taking pastries and the holes in pastries are things that the number of holes are things that would survive, after stretching. Like if I take a donut with one hole in it and I stretch it like this, well, the hole is a defining property, a topological property of the donut, of course. But if I tear it, now I've really changed things, and that's exactly what they're demonstrating here. But I am slightly concerned about their spelling. Okay, but no one's perfect. Okay? There's a few extra letters there. But where, I think it's a fair question at this stage, is that where is the topology coming from in this in these materials? Where is the topology? What is topological about them? How does that help to create the sort of interesting behaviors like the ones we highlighted about edge conduction versus bulk insulation? Well, I think that the beginning of topology in materials goes right down to their basic organization, you could say, at the atomic level. So what you see here are two, if you like, blueprints for and what is actually an everyday material. If you look locally at this, like if you see my cursor and you just look here, you'll see a silicon atom connected to two oxygen atoms. And I look here, again, silicon, there's connected to two oxygen atoms. You have this additional one sort of in between here, joining these two pieces. But that's the same everywhere, actually, in both of these pictures. So this is a form of you could say silicon dioxide, but even though locally they look the same, globally there's something different about them. Like if you stand back from it, like this one seems highly organized, and this one seems more haphazard. I hope you agree with me. So they're locally identical, but globally different, and that global difference actually leads to different properties of the materials. So I hope some of you are trying to guess what these are. Maybe you already know what these are. But this on the right, B here is glass. We could say it's everyday glass. Whereas this, more organized, more crystalline, more periodic material, however you want to describe it, is quartz, or a form of quartz. And actually this has emergent, because of this global, not only local, but global organization, this might enjoy some properties, some emergent properties that this actually does not enjoy. Something like, for instance, the piezoelectric effect might manifest here, but not here. Okay. And again, what I'm looking for are emergent behaviors. So so the organization of a material, not just the atoms, not just the ingredients, but the way in which they are organized locally and globally might lead to emergent phenomena. And so one of these phenomena, it could be electrical conductivity. Something that is highly disorganized is much less likely to conduct electricity than something that is highly organized, where electrons can enjoy a nice regular hopping distance. Okay, so I actually see this as the beginning of where shape, if you like. I hope this demonstrates that maybe shape is somehow important to physics. Okay. So to me, topology and periodicity, having a medium that's periodic or crystalline, crystal means repeating cells, if you like, are intimately linked. Now, to bring in more of the actual physics and thinking about, again, conductivity, so which is really the propagation of an electron across a medium. So an electron propagates in a way that might be described quantum mechanically by the eigenvalue problem for this particular operator. So I'll call this H for the Hamiltonian, and this Hamiltonian is a sum of two other operators. These are really kinetic and potential terms. So the Laplacian here, or minus the Laplacian, that's like the kinetic term or the kinetic operator. And V is the potential. And the kinetic part is always the same, if you like, but the V is where you can really design your material. The choice of V is really going to control the outlook, if you like, of your material. And when I say the eigenvalue problem, I mean, this is an operator, it's like a big matrix, and I'm looking for its eigenvalues and eigenvectors. The eigenvalues you could call energy levels, the eigenvectors you could call wave functions, and eigenvalue problem here is maybe just a polite term for the Schrodinger equation. That's really what we're talking about. But I'm maybe just, just telling you that, you could call it the Schrodinger equation, but really it's just the eigenvalue problem for this operator at the end. And again, as a mathematician, I like to sort of be as reductionist as possible about things. V is also, the potential is also your opportunity to interact with the crystal structure. So if we go, sort of back here, okay, so I've made this material that's periodic, let's say, that looks like A, but, how does the physics see the crystal? How does the physics, interact or remember that we're dealing with the crystal? Well, you build that into the potential. You would take a potential that repeats identically in each cell. And all of a sudden now you built in the structure of the crystal into your Schrodinger equation, into your operator. Okay, so I want to deal entirely with this scenario where V is always respecting some sort of crystal structure. So here's a picture of a square lattice instead of, say, a honeycomb lattice, like when we were looking at quartz over here. So this is also very regular. So A here is a two-dimensional, if you like, it's a film of material that's organized as a square lattice. And the thing is, if I really do have a potential that is the same in every cell, there is a sense in which I could say, well, maybe I could just focus on a single cell. Maybe all of the physics is contained in what's happening in a single cell. Well, if I do that, that means that, I could, the left edge of my cell and the right edge, let's pick a cell. The left edge of the cell and the right edge, and the right edge of the cell are really the same, because the right edge of the cell is really the left edge of the next cell, and these two cells are identical. So I could identify them, and same thing with the top and bottom edges. And if I do that, if I take out this cell and I identify the top edges, the top and the bottom and the left and the right, I'm going to get a torus. I'm going to get something that is topologically interesting, non-trivial, something with a hole that wasn't, that I didn't see before. So working on a single cell of a crystal is like passing to a topologically non-trivial position space. Now that's great. That's a very fine mathematical convenience, because depending on how much mathematics you've done, there's a lot of value in working on a compact space, a space that has a beginning and end like that donut, rather than something that's infinite. One simple reason is integrals behave much better when you have a start and an end than when you go off to infinity in many directions, right? Okay, so there's lots of great reasons to want to work on a compact thing. But this is just an affectation still, unless the solutions make sense on this compact domain. It's great that the equation makes sense on that compact domain, because the potential really only cares about a single cell. But what about the solutions? Do the solutions respect the crystal? Is it possible to completely determine a solution by what's happening in a single cell? That's a fundamental question. And the answer is actually generally no. However, the solutions are not too far off from being periodic or being sort of definable in a single cell in a particular sense. And this is due to Felix Bloch, who studied this actually almost 100 years ago in 1928, believe it or not. So what Bloch discovered at that time, working through some of the mathematics here, is that solutions to the time-independent Schrödinger equation for a periodic potential can be expressed in a basis of quasi-periodic solutions. So solutions that are almost periodic. And to illustrate that, okay, here's here's a two-dimensional space, a film, if you like, that I've covered in a repeating lattice. Okay, so I've covered with this crystal that's this repeating parallelogram. And the thing is that these solutions that Bloch had found, if I pick one cell as the fundamental cell and I solve the equations there and get my wave function, and I've gone phi sub n because I might have different functions for different energy levels, like different eigenvectors, and the x there is the position coordinate here. Then if I move to another cell, it looks like the same wave function, except it's been rotated by some phase factor, some e to the I something. And that e to the I something, that something part, is, if you like, is a function. It's like a circle-valued function. It's like a function that's within 0 and 2 pi. It takes values between 0 and 2 pi that depends on how I translate it. So this function I'm calling k in the picture. And the something that I translated by is this lambda here. So lambda has taken the x coordinate and dragged it sort of over here. Okay. If I like, I could have written lambda of x here because I'm really in a different position here. So this is really x after it's been translated by lambda, but it really is the same value as this. That's what I was going for here. But this part on the outside, this phase factor, this angle here is a function of whatever that lambda was that I used to translate me from here to here. And so a different lambda, would have a different angle associated with it. And this k is the machine that's turning translations into angles and telling me how much to rotate my solution. But in this sense, I basically do know what's happening from a single cell. I solve here, and all I need to do is keep track of how I rotate in any other cell. Basically, if I know the solutions here, I only need to know what k looks like over here. And so you can start to form a picture. So I told you that I could fold the real space, the space that's coordinatized by x. This is where the electrons are actually propagating into this torus. So this is the position space of the real space. But then there's this k space. So the choices of possible k's that I could have used for this rotation, for this twisting, this phase factor, whatever you want to call it, actually mathematically and very conveniently, the choice of all of these possible k's that tell me how to change translations into angles actually form an identical torus. And we call that the momentum torus or the phase space. Okay. Also, for those of you who are familiar with your condensed matter literature, you call it the Brion zone, if you like. But it's momentum space, and they're related by a Fourier transform, if you like. But the point is that you can pass to these k coordinates in the way I've sort of just described visually through this idea here. Okay, and the thing is, you can keep track of the k values. So I could pick, this k, this function k here. This is again the space of all possible k's that I could pick. I pick this k here. This is again a gadget for turning translations into angles. And then these are, if you like, the eigenvalues, the energy levels associated with that choice of k. If I were to choose a different k, then my eigenvalues, my energy levels might change a bit. And what I'm doing is I'm getting now sheets of energy levels that live over the momentum space. And this is really important. This is like the material analog of orbitals, in a single atom. You could talk, if I have a single atom, I can talk about energy levels, orbitals. I can talk about how far how energetic an electron is, how far it is from the nucleus. This is like the global version of that, these sheets that I'm building out of energy levels, as I vary K, are a global version of the orbitals of a that you would see in just single atomic theory. Okay, but here's for the whole material. Okay. Um, and then the ability to make these sheets of energy levels leads to pictures like this. Okay, so these are two very similar pictures. So here are like some K values on the horizontal axis. I can think about going maybe like a 90-degree angle somewhere on this momentum torus. So this is K from 0 to some pi over 2. And I can watch as the energy levels change. To keep things simple, I'm going to say that I have a tight binding model in which, I just have two energy levels, like a ground state, like a lowest energy sheet, and then one higher energy sheet. Okay. And so, here's my lowest one, and then here's my highest one. You could call these conductance and valence bands as well. There's other ways you can justify the two-sheetedness of this picture, but, I'll just keep it simple and say that this is working in a kind of tight binding model. What's different about these two pictures is that here there's a gap, and this mu, which is the Fermi level or the electrochemical potential. This right here is, if you like, determined by your actual atomic constituents. Over here, this mu is passing through the two types of sheets, the ground and the next one. So there isn't a gap in the same way as here. You could think about this mu as kind of like the high jump that an electron needs to go through to pass from conductance to valence. Here, it can't make the jump. It's too high. This is like the gap is too big, and this is like an insulator. And then this it can make the jump, and this is like a metal. So this is like the mathematical pictorial distinction, if you like, between insulator and metal. Like these pictures. These are pictures of what we call band gap structures. Again, for those of you who are experts in condensed matter physics or solid state physics, strongly correlated systems, this is bread and butter for you. Okay, you're just dealing with everyday band gaps. But for those of you who've never seen it before, this is like a picture in momentum space of the difference largely between something that insulates and something that conducts. Okay. And just to inject some reality into the picture, here's the famous, here's silicon, and here's its famous band gap, which you can see right here. But here I'm again literally working in K space, in K coordinates here, and here's our energy levels, and here's the gap, telltale gap of silicon. But what I have to emphasize is that these are just like 1D pictures in the sense of like I have a one-dimensional horizontal axis. I'm just going through a curve, a path of K values and making these pictures. But if I go back to here, this is a two-dimensional surface in the sense that its skin is two-dimensional. Okay, so there's maybe these are nice cartoons, but they're not global pictures that capture everything that's happening here. So, if you were to stand back from this and try and make a picture where the horizontal space was two-dimensional, more in keeping with the dimensionality of the momentum space, you might get something like this. And here in this picture, you see, this is, if you like, the conductance and the separation between conductance and valence, or between sort of the two types of bands. And here, this would be like the electrochemical potential or mu. And so what you can see are mostly gaps, but there are places, special points where there might be crossings. And this is where we start to see that the physics might be more complicated than just insulator, but there might be smaller regions, maybe lower dimensional regions that allow for some conductance. And this is where the beginning of topological materials really is, and some of the behaviors that I was mentioning earlier, where you might have some zones, some regimes, some subspaces, if you like, with a different conductivity profile than others. Okay, and I think for me, it's really about standing back and looking at the full picture instead of just these cartoons. Okay, so this is just a kind of quick walkthrough of again where topology shape enters the properties of physical materials, and why at a quantum level, in thinking about these momentum pictures that arose from trying to solve the Schrodinger equation, where the unusual physics might start to emerge. Okay. But I want to ask a naive question that a mathematician might ask. Can the position space be a curve of genus bigger than one? And genus is the number of holes in these surfaces. And by the way, curve here really means surface. It's just for mathematicians, a surface in counting in complex dimensions instead of real dimensions is like one complex dimension. Two real dimensions makes one complex dimension. Okay, like R2 is like C. So it's common. It's hard for me to escape my mathematical thinking that this kind of surface is like a curve, but that's only in complex terms. So I'll say, can the position space be a surface of genus G bigger than 1? So what I'm asking is in pictures is this question. On the left, could I replace the position space or the X space, the place where the electrons are propagating, or electron? This is really single electron dynamics, so don't get me wrong about that. But could I replace that with something that's two-holed instead of one-holed? Just, it's a kind of cute or naive question that a mathematician would ask. And then the later question is, if I could do that, what is going on the momentum side? Is there even a momentum space in any good sense? Well, here's an interesting fact. So to produce a genus G, like G-hold position space, out of 2D space, what you can do is tile it, make a lattice, where the individual cells are 4 G-gons, meaning that they have 4 G many sides. And that already checks out with the square business. Like a square has 4 sides, that's 4 times 1, and when I do the folding, I get a donut which has G equal to 1 whole. If I want to get octagons, for example, and we see hexagons in nature all the time, great, but octagons would be new. We don't usually see materials where they're arranged internally according to 8-sided figures. And I'm interested in 8-sided figures because 4 times 2 is 8. And that should give me a 2-hold surface. G would be 2 here. Okay. So that's interesting because I can get, from octagons, I can get genus 2-hold, but also octagons are not something that we see. So that would be like a new kind of physical material. Okay. So let's just think then, can I tile space, like 2-dimensional space? Can you tile the table in front of you with octagons? Well, if you try, you'll get something like this. This is not a good tiling because the octagons don't meet perfectly. They have all of these squares between them that you can't cover. They're like defects. Actually, in making a material, defects might be good. It might allow you to engineer, again, some interesting properties, physical phenomena that weren't there before. But you don't necessarily want this many defects. If this keeps going, there are infinitely many defects. Too many maybe to make good physics out of. So you might say that, okay, I can't tile the plane by octagons, and so I can't get a genus 2 position space. So game over. Mathematician or a geometer would not give up here and would do this. This is a tiling of 2-dimensional space by octagons. This is the geometric idea I wanted to sort of infuse into. If you take anything away from this talk, it's this. This is a tiling of space by octagons. Now, to you, it looks like, and to me, in fairness, it looks like these are sort of getting very warped. They're sort of degenerating as you go away from the center. Actually, they are all the same. They all have the same side lengths, the same angles, just in a different way of measuring. And this is where geometry comes in, as opposed to topology. According to a different way of measuring distance, sort of side lengths and angles, these are all regular, actually. So not through the Euclidean metric or way of measuring distance and angles that you normally use, but through the hyperbolic ones. This is called hyperbolic space. It's also called the Poincaré metric. Okay? So in some other world, these are all regular, okay, but not the Euclidean world. But this is a starting point. What I'm telling you is that if you're creative enough with how you measure distance and angle, then you can tile space by octagons, and then you can fold things up to make something actually that is genus 2. Okay, so that C here in this picture is the reduced position space where an electron might propagate if it were to live on a hyperbolic crystal. Okay. Okay, so I'm going to tile the hyperbolic plane by 4 g-gons, and I'm going to choose a periodic potential. Potential that is the same in every cell, okay, that repeats, that respects this hyperbolic crystal. And for those of you who care about a little bit more of the deeper mathematics, you could say that the translation group or the translation symmetry here is now non-abelian, it's non-commutative, which means that if I have 2 translations and I do them in different orders, that you might actually end up in a different place in the crystal. That's very different from what we were looking at before. And this kind of group is actually an example of what's called a Fuchsian group, for those of you who are, like mathematical terminology. But really, there's no physics, again, until we have an operator, until we have a Schrödinger equation. Because, there's a perfectly fine one. I told you I picked a potential V that's periodic. I just need to make sure that my kinetic term is properly adapted to this geometry. So it's not the Laplacian now, it's what's called the Laplace-Beltrami operator. And there's a little recipe for it here. Okay, but I'm just telling you that there is a good kinetic term here. And it just boils down to, can we solve this equation? Can I find eigenvalues and eigenvectors? Well, my collaborator, Joseph Macheko, who's at the University of Alberta, and I, a few years ago, we took a very particular tiling for which this octagon here is the sort of fundamental cell. And then what we did was we actually just did it numerically. We chopped this up into many, many triangles, numerically solved for the wave function here. And then, we were able to sort of extend this, to other cells by choosing K functions of our design, if you like. And so with no potential, which by the way is a kind of periodic potential because 0 is the same everywhere, this is what the energy levels look like. And you see things here that might look like gaps. And these are the wave functions as kind of color plots, over the cell. And then here with the red curves, this is where we turned on a non-zero but periodic potential, and you can see how they're perturbed now from the original blue ones. And here's color plots of the wave functions again. And so by the way, looking at the horizontal axis, this is going from 0 to pi. So this is like a full, a sort of half circle of K values presumably in momentum space. And this is just a picture of how we were attaching sort of the next cells, but you can see how they're warped by the Poincaré metric or the hyperbolic geometry. Okay. This was the paper that we wrote together called Hyperbolic Band Theory. This is where we sort of set out this. This is like the extension of Bloch's theory to the hyperbolic crystals. And there's still the question of if I had something like a genus G equal to 2 surface, is there a space of crystal momenta there? So like where do the K values live? What does this space look like? And the main takeaway here is that there's actually infinitely many momenta spaces. They're increasing in dimension and getting more and more complicated in their internal topology, if you like. This is at the left, this is the analog of the momentum space you've seen before. It's another torus. But the fact that the translations are non-abelian or non-commutative means that you have momenta of increasingly higher dimension. And that never stops. This is the 2-dimensional momenta, 3-dimensional momenta, and so on. And so guess what? That means that there's a band structure here over this torus as I move my K's around. There's another one here There's another one here. So there's actually infinitely many band structures that all at once conspire together to control the physics of such a material, which means that the opportunities for engineering in a very fine way the behaviors of the material, I could have a band gap here, I could have no gap here, I could have something that looks like a gap for the most part, but then has crossing points. Like I can have infinitely many of these happening at once and engineer a plethora of very fine, maybe extremely unusual conductivity behaviors, which seems like it might be useful in the creation of devices, again, extreme devices. This is a follow-up paper that Joseph and I wrote where we sort of really drilled down on these higher dimensional momenta. But the last thing I want to leave you with is the question of, can we make such matter? Is this just all a mathematical abstraction? Or to what extent can I maybe synthesize or construct a material based on these hyperbolic geometries? Well, the important thing is maybe to take a cue from quantum computing, where quantum computing, again, I make a superconducting chip that has these qubits. Well, what are these qubits doing? They are macroscopic devices. Josephson junctions, by the way, are a common way of making a superconducting qubit. But whatever you call them, they are macroscopic devices that are trying to mimic as much as possible the behavior of an electron or a two-level atomic system. Like an electron has spin up and spin down, or an atom with two energy levels. Again, another kind of tight binding atom. These are devices that are trying to be that, even though they're macroscopic, and they're trying to exhibit quantum behaviors, but in a macroscopic environment, if you like. Let's take a cue from that and say, well, maybe I can arrange features as atoms, or as something or things that are mimicking atoms, but arrange them in such a way that achieves or tries to simulate a hyperbolic geometry. So what you see here is a chip, but this chip is really a metamaterial. And this was constructed, this is based on a 7-sided septagonal lattice, which is basically the same thing for our purposes as an 8-sided lattice. But this is basically a hyperbolic material or hyperbolic metamaterial here. And this was, but this is constructed in exactly the same way as superconducting chips. So this is this would be operated, if you like, at sub 1 Kelvin temperatures. This is the lattice that it's based on. This was constructed by Alicia Collar together with Fitzpatrick and Hauk. This is when she was, I think, at Princeton, maybe finishing her PhD or postdoc. I don't want to get that wrong, but anyway, she's a professor in Maryland now. But this was an incredible a feat of nature, if you like. Well, ended up in Nature in 2019. So I can't escape that year for some reason. But this existed before Joseph and I mapped out the band theory of hyperbolic materials. But nonetheless, this is an attempt to make this kind of matter. Here's another attempt from a paper in 2022 from a different group. This is more of a room temperature breadboard experiment, but there's a kind of hyperbolic geometry going on here. In these experiments, there's some elements of hyperbolic dynamics detected, like signals propagating along hyperbolic geodesics, hyperbolic paths of least distance. But there was no observation in these experiments of a spectral gap. So let me conclude by saying that I've been working with a group at the Institute for Quantum Computing at Waterloo, led by Matteo Mariantoni, where we've been trying to basically do the same thing as what Collar was doing, just maybe with a little bit more attention to some ways in which the hyperbolic geometry is being encoded in distances, but also in couplings between features, coupling strength between features, and running under very controlled conditions in a dilution fridge, where we are actually seeing evidence of a spectral gap. So this is the sort of beginning of these experiments here. What you can see is some results of laps of photons around this ring through a vector network analyzer. But the key thing is that this past October we put out a paper where we really put forward these designs, discussed the experimental results, and showed that we actually do get what appears to be gaps in a spectrum. So you can see this sort of transmission versus frequency graphs here, where we see evidence of what would in K-space be spectral gaps. And what I want to say is that also not only did we do 8-sided, but also 12-sided lattices, which means genus 2 and for the first time genus 3. So this is probably, in our opinion, maybe the best evidence of being able to construct hyperbolic geometries that exhibit some of the behaviors that have been predicted theoretically, mathematically in the band theory. Okay, so these will be could become components or platforms for enhanced quantum computation in the future. So my PhD student Ahmed, who's in the bottom row here, and I have worked on paradigms for hyperbolic quantum error correction, how you might use such geometries to achieve better quantum error correction rates than in current superconducting quantum computers. Chris Xu in the bottom is the lead student from Waterloo on this project. Matteo is in the top row. You can see Alicia again in the top row, but also Joseph Macheco was there as well as other students and postdocs I've worked with. If you've liked some of the pictures that you've seen here, these were hand drawn by Elliot Kienzel, a former student of mine who's now at UC Berkeley doing his PhD. He was is a real wizard with iPad drawings and GoodNotes, and illustrated to great effect one of our papers, and those are the fancy illustrations you've seen here. You can't do this kind of work without funding, so we thank our funders as well as our industry partners, and that's it. Thank you very much. And realize we're sort of towards the hour, but very happy to stay and take any questions that anyone might have.
Thank you a lot, Professor Rayan. There was indeed some question in the chat.
Okay, great. Yeah, I can't
I
see
can
the
I'll
YouTube chat, but
it's okay. I'll read it. So the question
sure.
says from Pierre, it says, I was wondering if these geometric concepts will be more used to optimize physical hardware or mostly um, in the way quantum algorithms will be designed.
That's a great question, and I don't know at which point in the talk that was asked, but I guess some of my comments towards the end intersect with that. At this time, I've actually thought about both, the generation of quantum logic gates and hence quantum circuits and algorithms through such geometries, and quantum error correction, which you can think of as a kind of physical hardware optimization at the end of the day. Right now, I'd say the more promising angle is definitely the error correction, because there you can make a direct comparison with ordinary error correcting codes, and looking at comparing thresholds and rates of correction, if you like. And there's advantages, and this was known before me. It's just we sort of my student Ahmed and I did a very systematic approach to this, inspired by some of the designs here. But nonetheless, we sort of, I would say, validated or re-verified that, there are advantages to hyperbolic error correcting codes. In terms of generating new types of circuits and impact on quantum algorithms themselves, I think that remains to be seen. I don't think that, we can necessarily generate gates more efficiently than with current architectures. I think it's more about whether maybe one could, for instance, look at non-unitary approaches to quantum computing, where there is a bigger set of gates at one's disposal, and ask whether those are somehow more naturally generated from these kinds of devices or chips than the standard ones. That might be a place where one could look. But yeah, I would say that it's more about advantages with error correction at the moment.
Awesome. I have a question.
Sure, go for it.
So when I think of hyperbolic geometry, or something with a constant curvature, I think of maybe like a de Sitter or anti-de Sitter spacetime. So I was just wondering if maybe it could be used for some sort of quantum simulation applications in holography, for instance.
Yeah, amazing question as well. I would say yes. In some sense, we're working in ADS space here, if you like, and we're in negative curvature is a way to describe that we're working in hyperbolic geometry. And in some sense, yes, there is the potential for this to be a very low temperature as opposed to high energy tabletop method for trying to simulate things that would normally be at astronomical scales at very high energy in terms of, say, ADS CFT. So that is I think a promising direction here. I mean, it's something we've already anticipated. It's in some sense above my pay grade at the moment, but there's certainly interest in exploring that direction.
So what there's a couple other questions. So what future projects would be available for prospective research assistants or graduate students in your group?
Oh, yeah, great question. And always recruiting new people. I mean, we have a very large group here in Saskatoon at the moment. There's also the Waterloo group, of course. But one project is everything I've told you is in two dimensions. What about three-dimensional hyperbolic materials, just for example? Is there a band theory for them? Can you synthesize, construct artificial three-dimensional hyperbolic chips or devices or metamaterials? There's just one example of a potential project. There's a lot more that can be done, I think, in the quantum error correction space. If you like more the sort of applied quantum computing side and how it intersects with mathematical constructs, there's actually a lot that can be done here. But I would encourage, if anyone's interested, just to reach out to me and tell me what you're interested in. I can tell you what we're doing, and then we can see where that matches up.
So what would be the best way to reach you for a student?
Oh yeah, so there's an email on screen right now, which is the email for our research center, quanTA. So it's easy, quantum@usas.ca, but you can also email me directly, Stephen with a V, .Rayan, that's Rayan, extra A there, at usas.ca. Or just Google me, and I'm sure you'll get my professional, researcher webpage as more or less the top hit, and just find my coordinates there and just start a conversation.
And one last one. So what resources would you recommend for students to learn more about your research?
Oh, great. Yeah, you could start from, there's so many different ways to get into this area. I mean, you could start by just, learning more about quantum information and quantum computing. You could start from condensed matter physics, thinking about strongly correlated systems, and then going from there to topological materials, quantum materials more generally. If you're someone who's into experiments and device physics, looking at the different attempts that have happened so far to engineer these kinds of metamaterials, any of these are great starting points, and then we can converge from there. Ultimately, this is very interdisciplinary work. You don't have to be interdisciplinary at the beginning. You can start from any of these angles. But eventually, working in a group like mine, you'll sort of come out the other side, I would say, being very interdisciplinary, having an appreciation for the mathematics, an appreciation for the physics, an appreciation for theory and experiment, and also maybe being poised to work in an area like quantum computing, either at a theoretical level or potentially at an applied, more use case driven level.
Thank you a lot, Professor Rayan. And thank you again for presenting and all the participants. I also wanted to let you know that all the websites of Professor Rayan are in the bio of the YouTube, in the YouTube live, so don't hesitate to look at them if you're interested, as well as the contact information of SAC of the SAC is in the description of the YouTube video. So again, thank you a lot and have a good evening.
Yeah. No, thanks a lot again for both of you, Audrey and Ireneo, for convening this and managing the event. And thank you everyone who joined. If you have any questions, please just let me know. And thank you all for being really great, engaged students and taking part in CAP activities. I think that's awesome.
Thank you.